So basically what I do in the company is working on APT attacks and targeted attacks, big cyber criminal group activities or cyber espionage attacks. And my areas of interest are malware analysis and reverse engineering, also forensic analysis. Before joining Kaspersky Lab, I used to work in a local antivirus company overseas, doing rootkit analysis and kernel mode malware analysis and developing anti-rootkit tool. But since I joined the Kaspersky Lab company, I'm doing more threat intelligence and malware analysis as well. So moving on, let's talk about my presentation today. I'm going to talk about the attack which is called Shadowpad. First of all, we will see what Shadowpad is and why is it important. And then the story of the first case of Shadowpad that we discovered and worked on. Then we will see the technical details of the attack framework, which is a sophisticated attack platform. And then we will see some other supply chain attacks and other attacks related to Shadowpad, and also other similar malwares that I worked on. And we will see different similarities and differences between different cases of the Shadowpad attacks, and then, of course, the conclusion. So, first of all, Shadowpad is one of the largest known supply chain attacks. There was a backdoor implanted inside a server management software which was used by lots of customers all around the world. And when the backdoor, which was inside the software, was activated, it would let the attackers install more malwares on the system, on the victim system, and then also steal data, or they would have actually full access on the system, what they want to do. And it was very sophisticated. That makes the detection and analysis of the attack very difficult. So, what is the first case of the Shadowpad attack that we discovered? It was happening on a software from a company called NetSaran Computing. It's a company that provides secure server management solutions, and it's being used by telecommunication industry, financial industry, and lots of organizations, hundreds of organizations in more than 90 countries. How we started, how we know about the attack, it was not from the NetSaran Computer company itself, but it was from a financial institution. It happened in July 2017. During an investigation inside the financial institution, the security team realized that there is something suspicious going on their network traffic. So there was some suspicious DNS requests that they saw in their traffic. And because the system that the DNS request was originating from, it was a system responsible for doing financial transactions, it was very alarming for the company, and they immediately contacted us and asked us to help. So when we started looking at the network traffic, we saw something like this. If you notice, the domain name is very strange. It's a long, random characters, and it was happening on the network traffic from the system that I said it was a system responsible for financial transactions. This DNS request was even happening in a suspicious way. It was happening every 8 hours, and the security team had no idea what's going on. And also the packet that was sent to the server had some basic information about the system, username, domain name, and also host name of the system. So we looked further to understand what process is creating this DNS request, and we reached a process called X shell. If you see up in the list of processes, you can see X shell process. And then also inside that X shell process, there was a DLL called nsoc2.dll, which was the origin of the DNS request. But what was this DLL and this package? That's where we arrived at NetSaran company. The software package X shell was from this company that had their headquarters in US and South Korea. And the DLL and the software package was a legitimate DLL and legitimate software. So we immediately went to the contacted the software vendor and realized that it's not only this X shell package that's been Trojanized, there are also other packages as well. But all of the packages had the same nsoc2.dll infected library. So how we contacted the vendor and they took down the software, the infected software from their website was also interesting. It was in the afternoon, if I'm not mistaken, it was maybe even on Friday afternoon in South Korea, and we had to contact them immediately. So we sent one of our researchers that's based in South Korea to personally go to the vendor company and ask them to take that infected softwares down. And they immediately responded and removed the software from the system and replaced it from the server and replaced it from the older, with the older version. But then we had to look inside this nsoc2.dll to understand what's going on. If it's a legitimate library, how it's generating that DNS request. This diagram shows how the code was inside this library. There was a legitimate code, and there was a big amount of encrypted data with a small decryption routine. So, as I said, it was a very sophisticated attack platform, which has the first stage of shellcode, and then the second stage of shellcode, and then a number of different plugins that they put together with the attackers put together with the stage 2 inside the encrypted block of data that the stage 1 shellcode would decrypt. Looking deeper, what was the decryption routine? What you see here is the decryption routine for the that decrypts the second stage of the shellcode. So what this little code does, obviously it allocates some memory, and then through a small decryption algorithm with some specific constants, it decrypts the code. And then in the bottom you can see the line with if a call to the v3, which makes a call to the first byte of the decrypted code. So the payload was encrypted inside the code, and then how it was triggered was also interesting. It was triggered through one of the object auto-initialization of the C runtime code. So what that means is that the code was added to the library before the compilation, which was also interesting. So we had this idea, we had this assumption that maybe the software development framework was infected that made the library infected in this way, that the decryption code is inside the C runtime code, which means that even before the main job of the library starts, even before the main DLL function starts, the infected and the malicious code would run on the system. But going after the first decryption routine, the code was something like this. As you see, there is some part that I put in red, which shows a specific obfuscation technique. It's not very specific to this threat actor, but it's not a very common technique as well. So what the attackers does, they put two complementary jumps after each other. So it's actually a useless code because one of the jumps would get done anyway, and they both put to they both jump to the same address, and the address is one byte after the next byte. So what that means is that there's one extra junk byte inside the code, which makes the code doesn't look how it's supposed to look. So why they do that? Because first of all, it makes the disassembler and debugger disassemble the code in a wrong way. And then it makes the analysis more difficult, because if you use IDA Pro or you use other disassemblers, you may know you can see the code in a diagram mode or even in a C pseudocode mode. But in this case, it's not possible to do that. So you cannot see the flow, how the code flows. But again, it's easy to fix it. You just have to undefine one byte and define the next byte, and makes it appear like this. And then if you want to make it fully fixed, you have to remove that junk bytes from the code. And inside this code, it doesn't happen once, it happens a number of times. And because this is a piece of code that is decrypted and run in the memory, it's even a bit more difficult, because if you want to analyze the code and look at the code in a static way, you have to decrypt the code, dump the code, and then fix the code and have a look at it. So, but moving on from the obfuscation technique, let's get to the way that the attack platform works. So as you remember, we had the stage 1. But the stage 1 was doing some kind of validation from a C2 server, which the C2 server happens to be the same strange, random domain that you saw. But it was not completely random. It was based on the current month and year of the system, and somehow depends on the day as well. Like it changes every 10 days. It means that in 1 month they use 3 different domains to do the validation of the second stage. So the first stage creates this domain and then contacts the domain and gets the decryption key for the second stage. So as I said earlier, we realized that this attack is going on in July. We went and looked at we generated the domain for different times of the year, and then we realized that the attackers have registered domains from July till a few months. So it was like a relief for us that we realized that the attack has not been active much earlier, and it was active maybe from the beginning of July. But then if the attack gets, if the malware can resolve the DNS and get the decryption key, what is the second stage? The second stage is, even for myself, more interesting, because from a reverse engineer point of view, it had a specific structure for the executable files, which were the DLL files, the second stage, and all the plugins inside the encrypted code. So it was, I actually get to the structure of the plugins later. But what I want to say here is that the stage 2 code was working with different plugins that were inside the code to install the plugins and use the plugins. And each plugin had the same structure as the stage 2. Another specific part of this DLL, which was the second stage, was that it had some custom defined reason codes. So apart from the normal code numbers, there were some other code numbers from 100 to 104 as well. And the DLL uses these codes to initialize the plugins. One for initializing the plugin, one for returning the plugin ID, one for returning the plugin string name, and then one for returning the plugin function address table. There are also different plugins inside the code which the malware would fetch and install on the system if they need it. So there were different plugins inside this NSOC2.dll library. There was one plugin with and each plugin has a code and a name. First of all, there was one plugin with code 100 and the name root, which was the second stage itself. There was one plugin called plugins, which the responsibility was to install new plugins on the system. What it does, it looks for new plugins on the disk, on the special part of the system that the malware downloads new plugins to, and if there is a new plugin, it would initialize the plugin and install on the system. There was another plugin which was called config. The config would take care of a configuration block that had the C2 address and other information about the system and about other information that needs to connect to the server. There was another plugin called install, which again does some sort of installation on the system, which means that it either runs the plugins inside the memory of the current process, or it injects the code into another process on the system, which the process is indicated inside the config block, and then runs the rest of the attack inside that process. There was another plugin, online plugin, which takes care of connecting to the C2 server and getting commands that are meant to be for different plugins and dispatch the commands to the plugins. And then DNS plugin, which works and communicates with the server on DNS protocol. So I talked about the plugin structure a bit earlier, but the interesting part was that first of all, the attack platform is capable of running plugins in a standard DLL structure, but they had implemented their own structure for DLL as well. So how is this structure? The structure of the custom structure of their plugins is like, it's somehow similar to the standard P structure, but the header was different. If you know, there are lots of fields in the P header for the standard P structure, but the attackers removed all the unnecessary fields, and they just made a very compact header for the DLLs, which had some of the more essential fields of the P structure, like image size, image base, relocation section, virtual address and size, which is used for DLLs, and then import section, virtual address and size, address of entry point, of course, and then there was even a specific type of timestamp that they used to recognize the version of their plugin for themselves, or when it was compiled and when it's going to be used. And then the section headers. So I'm not going to talk about this, the structure of the attack platform anymore. Just to summarize the attack on the NetSarang company, the attackers got access to the corporate network sometime earlier in the year, and then they infected the software developer system, as we guessed earlier when we saw the infected DLL, and there was infected in a way that the linker of the system was infected, and when the software developer develops the code and wants to compile the code, the linker would add this malicious code and the decryption to the library. So we didn't stop investigating the Shadowpad attacks, but the case of the NetSarang computer was almost finished. I was working on the similar samples to find out what else is going on. Then in September, I'm sure most of you know about the CC Cleaner incident. It happened in September. There was another supply chain attack like what happened with NetSarang software package, but it was not, the code was not similar to the Shadowpad. Some of the techniques were similar, but not the code. So AUSCERT started investigating what was going on the CC Cleaner development platform, which was done through a company called Piriform, if I'm not mistaken. But the company was bought by AUSCERT sometime later, after the attack has happened. Actually, after the initial attack has happened, not when the CC Cleaner was infected. So researchers from AUSCERT started investigating what has happened on their system that made the attacker infect the CC Cleaner. And then after working for a long time on the systems and realizing what was going on, what was the initial phase of the attack and what happened on the system, they found out that there was one initial attack on some of the systems, development systems of the CC Cleaner, and then there was a second stage malware which was deployed on some of the systems. Also, there was a third stage that happened on some of the systems, which the third stage happened to be similar to the Shadowpad. With the structure that you see here, this is from the AUSCERT blog itself. It has the same code. It was actually another case of the Shadowpad attack with different plugins. So the AUSCERT researchers, they continued the research as well, like what we did. And they also found out that in South Korea and in Russia, some other Shadowpad attacks have happened as well. But it was completely irrelevant to the CC Cleaner. I'm just mentioning it to let you know how many different attacks has happened based on this platform. So what we also found was some samples of the similar threat actor of the Shadowpad attacks, which were compiled in 2015. So it means that it's been at least going on for 2-3 years, if you count 2018 as well, because I don't think the amount of resource, time, and money that's been spent on developing this platform is going to be stopped. So looking at the malwares from 2015 till 2017, over the time the attackers added more sophistication to the files. Like the obfuscation technique that you saw, or the first stage that did the validation through the C2 server, initial C2 server. But then different samples had different characteristics as well. First of all, the first stage was we only saw the first stage on the NetSarang attack. The other samples that we saw, they didn't have that kind of validation through an initial C2 server. So the stage 2 and the plugins would get decrypted and installed on the system without any contact to the initial C2 server. And then there was other plugins. There was the execution of the plugins that was going on with different set of plugins, which we will see later. There were new plugins that we discovered through investigating the old samples. There were other plugins, disk, process, service, register, and shell. They were not present inside the NetSarang attack. A few of them were present inside the attack that AWASP found on their system, but not all of them. So it means that there might be even more plugins developed for this platform, which the attackers use in different cases. Looking at the decryption routine from other samples, you can see that the decryption routine is quite similar, but some of the constants are different. Like the one in the bottom, the constants, some of the constants are very small, but there's one big constant as well. So the decryption algorithm is also different. It means that the detection of the attack is more difficult because there's no same decryption routine for all the samples. So as we saw in NSOC2.dll file, the decryption, the malicious decryption routine was triggered through the C runtime code, but it was not the case in other samples that we investigated. There were some samples that the DLL module of the first stage would hook the loader module of itself. How it does, if you look at the first image, you can see that there is a hook function, which I renamed to hook function. And if you are familiar with the inline hooking, to do inline hooking, you calculate the difference between the address of the memory that you want to hook with the hook function. And then you put the, so to make the inline hook, first byte is the jump code, which is E9, as you see in the bottom, and the rest is a D word that contains the difference address to jump. But then when you go in, so it means that when the execution flow reaches the address that it's been hooked, it will jump to the hook function. But the hook function, if you look, is exactly similar to the decryption function that we saw earlier. So the last thing I want to share is that who is behind these attacks. First of all, we are not yet 100% sure which threat actor is behind the attack, but we saw different similarities with the plugx samples and Vinti samples. So initially, one of the C2 addresses of the NetSarang attack was used in a very old plugx sample. And then we realized that the similar encryption algorithm or decryption routine was used in a variant of plugx as well. And also, some of the plugx samples had the similar obfuscation technique, as you see here. This is a screenshot of one of the plugx samples. Apart from that, AWASP had concluded somehow the same thing, that the attack was coming from Chinese-speaking actors that use plugx and Vinti malwares in the past as well. Conclusion. If the attack on NetSarang was not stopped early, and if the company didn't respond early to take off the infected software on their system, it would infect lots of organizations around the world. That's how happens in supply chain attacks. Like CC Cleaner, it was used by more than 2 million users. Of course, fortunately, not many users had the second stage malware, but 40 plus users had the second stage malware on the system based on AUSCERT analysis themselves. So it's important to realize that the amount of energy and money and resource and skills that was put to develop this kind of sophisticated platform is of course going to be used a lot again. And as these two cases showed, they're going to use it in supply chain, which makes it even more dangerous. So it's important to be aware of the structure and the TTPs of the attacks, and be cautious about the software development platform. Thank you, and if you have any questions, please feel free.
Thank you very much. There were some crazy reversing skills there too. Thank you. Are there any questions from the floor at all? There were no questions online. Alrighty, I think we'll leave it there then. Actually, no, I have a couple of questions for you.
Sure.
How prevalent do you think these supply chain attacks are? Are you seeing them increase or not?
Definitely with these two big cases, I think that it's increasing. Because, of course, when the attackers can go after the supply chain, which in fact, with one attack, they can infect millions of organizations or individuals, why would they go after each individual or each organization individually? Yes, definitely we see a rise in supply chain attacks.
And does it generally come as a surprise to the companies? Obviously, it is a surprise, but is it something that they look into from a cyber security standpoint? Do they get pen testing, or do they look into these kind of issues?
I hope they do.
Okay. Well, thanks again, and thank you very much. Noushin Shabab, thank you very much.